So, hello everyone, and welcome to the Bangalore Theory Seminar. Today's talk on equivalence test for read-once arithmetic formulas will be given by Bhargav. Bhargav is a third-year PhD student at the Indian Institute of Science and is advised by Professor Chandan Saha. Prior to this, he obtained his master's in technology at IISc itself, where he was the recipient of the CSI medal for the best MTech CSE student for the year 2019-2020. His research interests lie broadly in computational complexity theory, and in particular algebraic complexity theory, an area of theoretical computer science which focuses on the computational aspects of algebraic objects like polynomials and multiple variables. With this, I hand it over to you.
Thanks, Agrim, for the introduction. So, as he said, today I'll talk about equivalence tests for read-once arithmetic formulas, and this is joint work with Nikhil, who was a PhD student over here, and Professor Chandan Saha, who is my advisor. So let's start. So I'll start by defining arithmetic circuits and formulas. So arithmetic circuits are algebraic analogs of Boolean circuits, and they're a natural model to compute polynomials. So here is what an arithmetic circuit looks like. It is a directed acyclic graph whose nodes are gates, whose edges are wires. The inputs of the circuit are variables or field elements, and all internal nodes are either labeled by a plus symbol, so they are a sum gate, or labeled by a product symbol, so they are product gates. Every circuit has a unique output gate, and this is the gate without degree 0. A circuit computes a polynomial naturally. For example, every plus gate computes the sum of its inputs, and every product gate computes a product of its inputs. The polynomial computed by the circuit is just the polynomial computed by the output gate. Arithmetic formulas are special types of arithmetic circuits, and an arithmetic formula is an arithmetic circuit whose underlying graph is a tree. So, for example, this circuit is not a formula because of these edges colored in red. As you can see, some gates have out degree 0. On the other hand, this arithmetic circuit is a formula because every gate has out degree 0 and the underlying graph is a tree. So in this work, we focus on a special type of arithmetic formulas. So let me define those now. So these formulas are called read-once formulas, or ROFs for short. Read-once formula is a formula in which every variable labels exactly one leaf. So for example, the formula given over here is a read-once formula because, as you can see, every variable is in just one of the leaves. And while read-once formulas are a very simple model of computation, they have been studied extensively in both the Boolean as well as the algebraic settings. And in particular, in the algebraic settings, we know of PIT and learning algorithms for read-once formulas. And in this work, we consider another natural problem for read-once formulas called the equivalence test problem. So before I define this problem formally, I would have to define what equivalent polynomials are. So let us suppose that we have two polynomials, f and g. Both are in n variables x1 to xn and over a field f. If you're not comfortable with fields, just assume that f is either the field of complex numbers or real numbers. Then we say that g and f are equivalent to each other if there exists an invertible matrix A and a translation vector B, so that g can be obtained from f by evaluating f at ax plus b. So g can be obtained from f by replacing the variables x1 to xn by affine forms L1 to Ln, so that the linear parts of L1 to Ln are linearly independent. Now it's easy to see that if g is equivalent to f, f is also equivalent to g. So this is an equivalence relation. Here's an example of equivalent polynomials. So the polynomial g, which is the sum of 2x1 squared and 2x1 x2, is equivalent to the polynomial f, which is x1 squared plus x1 x2, because I can write g as x1 squared plus x1 times x1 plus 2x2. So I obtain g by replacing x1 with x1 and x2 with x1 plus 2x2 in f, and it's easy to see that the linear forms x1 and x1 plus 2x2 are linearly independent. Now, if we have two equivalent polynomials, they are essentially the same up to a change of the coordinate system of the underlying variables. So when I apply an affine transformation ax plus b to the variable set x, what I'm just doing is I'm just changing the coordinate system of x. So for example, over R, the field of real numbers, if f looks like this, g would look something like this. Now, a natural computational problem about equivalent polynomials is the polynomial equivalence problem. And throughout the talk, I'll call this problem P for short. But the problem is as follows. Given two n-variate polynomials f and g, we are supposed to check if f is equivalent to g or not. And if it is equivalent, we are supposed to output an invertible matrix A and a translation vector B so that gx equals to f of ax plus b. Now, over here, what do I mean when I say that we are given two polynomials, f and g? There are multiple models of inputs. Sometimes the input is given as list of coefficients. Sometimes we are given arithmetic circuits computing f and g. And sometimes we are also given black box access to f and g. What do I mean by black box access to a polynomial f? I mean that let us suppose that we want to evaluate the polynomial f at a point A. Then by black box access to f, I mean that we can do this evaluation in unit time. Now, polynomial equivalence is a natural isomorphism problem for polynomials. In fact, sometimes this is also called the polynomial isomorphism problem. And it is also related to several other problems, several other isomorphism problems, like graph isomorphism, algebra isomorphism, metric space conjugacy and isometry, group isomorphism for certain P groups, three tensor isomorphism, and trilinear form equivalence. Now, what do we know about the complexity of this problem? Well, over finite fields, we know that P is in the intersection of NP and coam. And as a till date, we do not know of any sub-exponential time algorithm for this problem. In fact, this problem is believed to be hard in the general case. And there is even a crypto system relying on the supposed hardness of this problem.
The complexity class coam.
Okay, so do you know of interactive proofs? Okay, so basically it's this. There is an all-powerful prover, and there is a verifier which sends random question, just one random question to the prover. And the prover gives us one reply. And using just this one reply, he's supposed to convince the prover of some, let's say, some theorem. So this class is a class AM. And the class coam is just the following. If a language L is in AM, its complement is in coam. Yeah. So yeah. And since P is thought to be hard in the general case, people have naturally studied a special case of this problem. And this special case is a setting in which one of the two polynomials, that is f or g, belongs to a well-defined polynomial family or a circuit class. And this special case is called the equivalence test problem. So let me now define the equivalence test or ET problem formally. So for a so the definition is as follows. Given an n-variate polynomial f, check if f is equivalent to g, where g comes from script C for a well-defined polynomial family or circuit class scripts. If yes, as usual, we are supposed to output an invertible matrix and a translation vector such that gx equals to f of ax plus b. Again, when I say that we are given a polynomial f might be given either as a list of coefficients, or we might be given an arithmetic circuit that computes f. But in most cases, when this problem is considered or studied, f is given as black box access. And this is also the case in our work. Now, because script C is a well-defined polynomial family or a well-defined circuit class, we can expect ET for script C to be potentially much easier than the general PE problem. And this turns out to be the case for some polynomial families or circuit classes script C, but like ET for script C can still be quite non-trivial and difficult. The ET problem has been studied extensively for several polynomial families. For example, it has been studied for the polynomial families like power symmetric, elementary symmetric polynomials, sum product polynomial, determinants, permanents, iterated matrix multiplication polynomials, design polynomials, continuance, sum of univariates, and Reed-Evans alternating normal forms. And in this work, as I said before, we study the ET problem for ROFs. And to the best of our knowledge, this work gives the first efficient algorithm for ET for a circuit class with unbounded depth, degree, and fan-in. So the fan-in of a circuit is just equal to the maximum of the fan-in of its gates, and the fan-in of a gate in the circuit is just as in degree. So now let me state our results formally. We have two results. The first one is for ET for ROFs.
Can you go back one
Yeah.
slide?
Okay. Yeah, so the first result is about ET for ROFs, and the result is as follows. There is a polynomial time randomized algorithm with oracle access to QFE. I'll tell you what it is in a while. That takes input black box access to an n-variate polynomial f, which is equivalent to an unknown ROF, and outputs an invertible matrix A and a translation vector B, so that f of ax plus b is an ROF. So over here, QFE stands for quadratic form equivalence. I'll talk about this in a while. This result does not work over all fields. There are some restrictions on the characteristic of the field. For example, it either has to be 0 or greater than n square, and the size of the field also has to be like at least n to the 13. Yeah.
What is the strength of the black box access when compared to the other kinds of access? Is this the strongest one?
For example, black box access is much more efficient compared to giving you the polynomial as a list of coefficients, because like a polynomial in n degree, polynomial in n variables of degree d can have like order n to the d monomials, right?
Right.
So black box access is very efficient compared to giving as a list of coefficients. No. So let's say I want to evaluate a polynomial given as a list of coefficients at one point, right? That would itself take exponential time. But in black box access, if I want to evaluate at one point, it's just unit time, right? Yeah. Right. And like it is also more efficient compared to circuit representation, because in the circuit representation, you have to do some extra work. In particular, you have to evaluate the circuit manually, right? I mean, right. And in some cases, like the evaluation the intermediate states might blow up. So you might have to go modulo some large prime or something like that. Yeah. So this basically pushes everything in.
What is theorem 1 exactly saying? I mean, where is the part of G is?
Oh, so G is an unknown RO.
Oh.
Yeah.
Okay, that is
right.
the G. Okay.
Right. So we don't know what G is, but we know it comes from this class ROFs. Yeah. And so now since f of ax plus b is an ROF, and we have known how to reconstruct or learn ROFs in polynomial time for a very long time. So not only are we able to output a fine transformation that maps f to an ROF, we're also able to learn a circuit for f of ax plus b and therefore a circuit for f. Right. So this is sort of a learning algorithm as well. Now let me talk about our second result. It is for the problem of P for ROFs. However, this result just works when the field is either the field of real numbers or rational numbers. And the result is as follows. There is a polynomial time randomized algorithm, again with oracle access to QFE, that takes input black box access to two n-variate polynomials f and g, which are equivalent to two unknown ROFs, and outputs an invertible matrix in a translation vector such that gx equals to f of ax plus b, provided such a and b exist. So what this is saying is that if g and f are equivalent to each other and also equivalent to ROFs, then we are able to find a and b. And so let's say f being equivalent to an unknown ROF means there exists a C1, which is an ROF. So that f equals to C1 evaluated at, let's say, bx plus d.
Same.
Right. Okay. For some invertible matrix C translation vector d.
They need not be equivalent to each other, right?
Right. Yeah.
They are, you're taking.
Yes, if they are, we are able to output a and b. And I mean, okay, no, them not being equivalent is not a problem, because assume they're equivalent. What will your algorithm do? It would output some matrix, some translation vector. Just do a PID. Just check if the two polynomials are equal or not. Yeah. So you can just assume they are equivalent. Yeah. So this algorithm, as well as the algorithm before this, used oracle access to QFE, that is quadratic form equivalence. The question is this necessary? Well, it turns out it is yes. And I'll talk about this in a minute. But before that, let me just say that oracle access to QFE is a mild assumption, because we know of polynomial time algorithms for QFE over the field of complex numbers, real numbers, and finite fields. And over field of rational numbers, we know that QFE is equivalent to integer factor. So now that I've stated our results, so let me motivate the problems. The first motivation is for the P problem for ROFs, and this comes from generalizing QFE significantly. Let me first define what quadratic forms are. Okay, yeah, so Rahul is asking, given black box access, can we obtain other representations of the polynomial? Well, let's say you want the representation as a list of coefficients. So since in the worst case, that representation itself is going to be of exponential size, given black box access, you can obtain that representation just by interpolating the polynomial. So going from black box access to list of coefficient representation takes exponential time, but if the size of that representation itself is exponential, that's not bad, right? That is sort of required. So going from black box to this list of coefficients representation is fine, but the problem of going from black box representation to a circuit representation is called the reconstruction or learning problem for that circuit class, and we don't know how to do that generally for like a lot of circuit classes. Basically, we can only learn some very restricted circuit classes, but for ROFs we can do that. Yeah.
There's a notion of approximation here between two functions which you can construct.
No. So there is no like notion of approximation, and that's for a good reason, because let's say I give you two Boolean functions and n variables. Okay.
Yeah.
They might be different, but still they might be same at all the points except one point, right? So unless you make exponentially many queries, you can't differentiate them. But for polynomials, two polynomials are different, are like very different from each other, right? Provided the field is large enough. So yeah, I mean, given a polynomial, learning it exactly makes sense. Yeah. So yeah, a quadratic form is just a degree 2 homogeneous polynomial. For example, x1 squared plus x1 x2 is a quadratic form. And quadratic form equivalence, or QFE, is just the P problem when f and g are both quadratic forms. Now, quadratic forms are one of the few polynomial families for which we can do P efficiently. And one of the reasons for this is that quadratic forms have a very nice canonical structure. For example, let's just focus on the field of complex numbers. So if f is a quadratic form in n variables over the field of complex numbers, then for some m less than or equals to n, we can show that f is either equivalent to the sum of x1, x2 up to xm minus 1 xm, or f is equivalent to the sum of xm square and x1, x2 plus up to xm minus 2 xm minus 1. And in fact, for simplicity and for a very good reason, we can just assume without loss of generality that the first case holds. Now notice that this polynomial, the sum of x1, x2 plus up to xm minus 1 xm, is a Redound's formula. This is what its formula looks like. And so our second result, which is P for ROFs, is a vast generalization of QFE. And this is one of the motivations for studying this problem, P for ROFs. Now, to quickly compare QFE with P for ROFs, in QFE, we know the ROF, it's the one that I just showed you. And we also know that the degree of the polynomial ROF is just 2. But in the case of P for ROFs, we don't know what the ROF is. We don't even know what its degree is. So as you can imagine, like P for ROFs is like significantly more difficult than QFE. The second motivation comes from generalizing ROF reconstruction. So ET for ROFs is just a learning problem, but for the class of polynomials equivalent to ROFs. So as I mentioned before, a learning problem for a circuit class script C is the following problem. Given black box access to a circuit C from script C, learn C, that is output a representation of C. Now we have known, yeah. Right, so that is again, you are asking this for the following question, right? Given C, learn C approximately.
Yeah, in some sense.
Right.
But is there any sense that makes sense?
I mean, you can probably do it, but it makes much more sense to learn it exactly because it's very far from other polynomials.
And
Yeah.
that's the case for all families.
All polynomials. Basically, it's just a Sparse lemma, right? Yeah, if f and g are not the same, then f minus g is non-zero. And put a random point with very high probability, you will be able to say that f and g are different. Yeah. I mean, okay, the size of the field has to be large, but yeah, apart from that, it's fine. So yeah, we have known of polynomial time algorithms for learning ROFs for quite some time in both the Boolean and the algebraic settings. And so it's natural to wonder that if we can learn circuits from the circuit class script C, can we also learn circuits from polynomials equivalent to circuits in script C? Because as I said before, if two polynomials are equivalent, they're essentially the same up to a change of the coordinate system. So I mean, if I can learn a polynomial f, I should probably also be able to learn a polynomial equivalent to f. Because morally speaking, that is just equivalent to learning f and that coordinate system. That's just it. The third motivation comes from taking a step towards learning formulas. Now, it is believed that learning formulas in the general case, in the worst case, is hard. So people have naturally focused on learning random formulas. So let me first define what a random formula is. So here's how you construct a random formula. You pick a tree structure arbitrarily. Then you label all the internal nodes with plus and product symbols arbitrarily. But in the leaves, you put random affine forms. Now, it turns out that if the number of leaves of the formula is less than the number of variables, then a random formula is equivalent to an ROF with high probability. And this is just because random affine forms are with very high probability linearly independent.
The affine forms are random.
Okay, so what does an affine form look like? It's a1 x1 plus up to an xn plus a0, right? Just pick a1 to an randomly from, let's say, a large enough subset of the field if the field is infinite. So this problem of learning random formulas has been considered before. In particular, Gupta, Kayal, and Shah give an efficient learning algorithm when the tree has alternating levels of plus and product gates and is a complete binary tree. And ET for ROFs also gives us learning for random formulas, but over here, the tree of the formula can be arbitrary, but we can have at most n loops. So now that I've motivated the problem as well, let me talk about some of the proof techniques that we use to prove our results.
So can you go back? So what is the efficiency here of the reconstruction algorithm depending on the depth and?
Okay, so for ROF, for like learning polynomials equivalent to ROFs, depth is not an issue because like since every variable labels at least exactly one leaf, the depth of an ROF can be at most n. So we just need to worry about one parameter n.
Yes.
And in the work of Gupta, Kala, and Shah, it's okay. So the algorithm is polynomial in the number of variables and depth. Yeah. So I'll just talk about how we prove our first result, that is ET for ROFs, because P for ROFs almost reduces to ET for ROFs. Okay, so let's start with a simple example. Let's consider this polynomial called the sum product polynomial, or SP, which is just the sum of as many variable disjoint monomials of degree d, where d is at least 3. Now notice that this is a very special ROF, and the ET for this polynomial uses the Hessian determinant. So recall that the Hessian of f is just the matrix of the double derivatives of f. In particular, the row index by the variable xi and xj is just the double derivative of f with respect to xi and xj. And the Hessian determinant of f is just the determinant of this matrix. Okay, so before we analyze the Hessian determinant of the SP polynomial, let us just analyze the Hessian determinant of this monomial mi, which is just the product of xi1 to xid. Okay, so if d equals to 2, it's just a quadratic form. Yeah, I mean, then you don't use the Hessian determinant, you use some other techniques. And the reason you don't use Hessian determinants is because the Hessian doesn't give you any information, right? Yeah. Yeah, so let's look at the Hessian of this monomial. So the Hessian of this monomial looks as follows. All the diagonal entries are 0, because a diagonal entry is just the derivative with respect to the square of a variable, right? But over here, like this monomial is multilinear, so the derivative of this monomial with respect to the square of a variable would be 0, right? So the diagonal entries are 0. What about other entries? So if the entry is indexed by the variable xij and xij prime, then it is just mi divided by xij prime, because that's how a derivative of a multilinear monomial looks like. This is what the Hessian looks like. So what about its determinant? Well, to evaluate its determinant, what we can do is we can take out the variable xij common from the xijth row and the xijth column. That is, we are taking it out common twice. And if we do this for all the variables, what we would end up with is we would end up with this factor 1 over mi square, and then a determinant of a matrix whose diagonal entries are 0 and all other entries are just this monomial mi. Now we can also take this monomial mi common from every row. The Hessian is a d cross d matrix, so we would take it out common d times, but there is this -2 over here because of this mi square in the denominator. So we get mi to the d -2 times the determinant of this matrix, which is just zeros the diagonal one everywhere else. And it's pretty easy to show that the determinant of this matrix is just -1 to the d -1 times d -1. So the Hessian determinant of this monomial is non-zero, and it looks exactly like this. Now, what about the Hessian of the sum product polynomial? So notice that if I is not equal to I prime, then the monomials product j in d xij and product j in d xi prime j are variable disjoint. That is, the double derivative of the sum product polynomial with respect to xij and xi prime j prime is 0. And because of this reason, the Hessian of the sum product polynomial is a block diagonal matrix whose diagonal blocks are the Hessians of the monomials m1 to ms. And therefore, the determinant of the Hessian of the sum product polynomial is just the product of the Hessian determinants of these monomials, and that is just alpha for some constant alpha times product I in S, product j in d xij to the d -2. In particular, note over here that every variable in the sum product polynomial appears in this Hessian determinant. Now, okay, why does the Hessian determinant of the sum product polynomial help us in doing ET for the polynomial? The reason is the following. It is known that if f is equivalent to g, that is, if f is equal to g of ax plus b, then the Hessian determinant of f is the determinant of a squared times the Hessian determinant of g evaluated at ax plus b. And since a is invertible, this number is non-zero. So Hessian determinant of f is, so we can get information of the Hessian determinant of f from the Hessian determinant of g. So in our case, we have an f which is equivalent to the sum product polynomial. So let's say that this f is sp of ax plus b. And the Hessian determinant of f is just alpha times the determinant of a square times the product over I in S j in d of Lij to the d -2, where Lij's are affine forms that ax plus b maps the variables xij to. So basically, this polynomial has all the information that we want about ax plus b. So by just computing this Hessian determinant of f and factoring it, we can get an invertible matrix B in a translation vector D, so that f of b inverse x minus d is a sum of variable disjoint monomials. That is, f of b inverse x minus d looks like sum over I in S of alpha I times product j in d of xij. Then what we can do is, this is a sparse polynomial, so we can interpolate this efficiently and find out the alpha i's. And once we have found out the alpha i's, we can absorb these alpha i's in the matrix B. And once we do that, f of b inverse x minus d would just be the sum product polynomial. So we have found an affine transformation which maps the polynomial f to the sum product polynomial. So this completes the ET for the sum product polynomial. And this ET is due to Kayal. Now, before I tell you how to do ET for a general ROF, let me first establish some terminology. So here's what an ROF looks like. We can assume without loss of generality that it has plus gate at the top and alternating levels of plus and product gates. Also, we can assume that there is at most one variable directly connected to every plus gate in C. So you don't have any plus gate with two or more variables directly connected to it. And F, which is equivalent to C, is just obtained by replacing the variables by affine forms. Now, what I'll do is I'll call these ROFs T1 evaluated at L1. I would call T1 to TS evaluated at their respective affine forms the terms of F, and I'll denote these by T1 hat to TS hat. So in the simple example of the SP polynomial, we were able to make the terms of F variable disjoint by simply analyzing the factors of the Hessian determinant of F. The question is, can we do this for a general polynomial, for an F equivalent to a general ROF C? So before we answer this question, let me first take a quick detour and tell you about what essential variables are, because we would need these to answer the question. So for a polynomial F, the number of essential variables of F, denoted by NESS of F, is this thing. It's the minimum over all invertible matrices of the number of variables in F of AX plus AX. That is, the number of essential variables of F is M if there exists an invertible matrix so that F of AX has exactly M variables, and for no invertible matrix B, does F of BX has fewer than M variables. So this is sort of the minimum you need in any polynomial equivalent to F. For example, the polynomial F equals to x1, x2 plus x1, x3 plus x4 square has three essential variables because that polynomial is just x1 times x1 plus x2 plus x4 square. And we can map x1 to itself, x3 to itself, x4 to itself, and map x2 to x2 minus x3. Now this map is invertible, and F of AX is just x1, x2 plus x4 square. And it's also easy to show that for no invertible matrix B, can you drop below three variables? Now, what do we know about essential variables? In particular, we do know of some computational facts about essential variables. In particular, we know that if F is a degree D polynomial, for a field of characteristics 0 or greater than D, then the number of essential variables of F is just equal to the dimension of the space of partial derivatives of F. Also, using this relation between the number of essential variables in the space of partial derivatives, we can define what do we mean by a set of essential variables of F. So if partial derivatives of F with respect to Z form a basis of the space of partial derivatives, we would say that Z is a set of essential variables of F, or simply that the Z variables are essential for F. Now, we know that given black box access to F, we can find out the number of essential variables of F in polynomial time. And this is because of the above fact. Why? Because given F, we can get black box access to all of its partial derivatives. And then once we have black box access to a bunch of vectors, it's easy to find what is the dimension of the space spanned by those vectors. And that is exactly equal to the number of essential variables of F. Moreover, Kayal in 2011 also gave a randomized polynomial time algorithm to find an invertible matrix A so that F of AX has only essential variables. That is, F of AX removes all the non-essential variables. Sorry, A removes all the non-essential variables from F. And this A is again obtained by using the fact 3. In particular, this A is just obtained by using the linear dependencies among the partial derivatives. So I'll not tell you exactly what A is, but yeah, it's obtained like this. So the message is we can not only compute the number of essential variables of F, but we can also remove all the non-essential variables efficiently. And we crucially use this. So now let's come back to the question that we had. The question was for a polynomial F, which is equivalent to an arbitrary ROF C, can we make the terms of F variable disjoint? Now, Kayal in 2012 gave a rudimentary approach for this problem. And what he proved was the following. Suppose that F is equivalent to G, that is F is G of AX plus B, and G is a sum of G1 and G2, where G1 and G2 are variable disjoint polynomials. Then there is a randomized polynomial time algorithm to find an invertible matrix B, so that f of bx is equal to f1 plus f2, where f1 is equal to g1, f2 is equal to g2, and furthermore, f1 and f2 are variable disjoint. However, this algorithm only works when the number of essential variables of the Hessian determinant of G is n. That is, every variable that appears in G is essential for its Hessian determinant. So in our case, f is equivalent to c in ROF, and c is just a sum of t1 to ts. So f is equal to t1 plus up to ts. So over here, g1 to gs are t1 to ts, and t1 to ts are variable disjoint. So if all variables in C are essential for its Hessian determinant, then using the lemma that I just showed you, we can make the terms of f variable disjoint. So the question that we now need to answer is, are all the variables in X, that is, are all the variables that appear in C, essential for the Hessian determinant of C? And even before we can answer this question, we first need to ask ourselves, is every variable that appears in C also present in its Hessian determinant? And is this polynomial even non-zero? If the Hessian determinant is 0, we can't do anything. We don't get any information. And when we try to answer these questions, we come across two hurdles. The first hurdle is that there are ROFs for which the Hessian determinant is 0. For example, the Hessian determinant of x1, x2, x3 plus x4 is 0. Why? Because take the derivative of this with respect to x4 and any other variable, it's going to be 0. So in this case, we get no information about A and B. There is one more hurdle. Let's say we are somehow able to overcome hurdle 1, or let's just say we ignore all the ROFs for which the Hessian determinant is 0. Even then, there are ROFs such that not all variables present in them are present in the Hessian determinant. For example, consider this ROF, which has 8 variables. However, it's easy to show that its Hessian determinant is just x1 squared times x5 squared. So only 2 variables appear in it. Therefore, at most 2 variables can be essential for it. And in this case, we can only hope to get partial information about A and B from the Hessian determinant of F. Now, suppose that we are somehow able to overcome these 2 hurdles. Then what can we do? How can we proceed with the ET for ROFs? So as I said before, if we are somehow able to overcome these hurdles, then using Kayal's approach, we might be able to find an invertible matrix B so that the terms of f of bx are variable disjoint. That is, f of bx looks like this. And let's suppose that the variable sets of these terms are x1 to xs. Now what we can do is, we can find a1 to a2 to as, so that if I replace x2 by a2 and up to so on up to xs by as, then this entire thing, so that is the sum of all the terms except the first term is 0. So now what we get is black box access to the first term of f of bx, right? And then we can factorize this term and recursively perform ET on its factors. So yeah. Okay, so what we are doing is we are somehow finding variables a2 to points a2 to as, so that if I replace x2 by a2 and xs by as, then f of bx at x1 comma a2 to as is just t, the first term. So the sum of other terms at a2 to as becomes 0. Yeah. So I haven't told you how do we find this, but we just find this somehow. So yeah, if we can find this somehow, we can get black box access to the first term. And once you have black box access to a term, factorize it to ET on its factors. So if we can do this, here's a high level sketch of a recursive algorithm that we can get. First, find an invertible matrix so that the terms t1 hat bx to t hat s bx are variable disjoint. Then somehow find their variable sets x1 to xs. I'll tell you how do we do this towards the end of the talk. Then once we have found out these variable sets, obtain black box access to each of these terms. And once you have black box access to these terms, recall that these terms are like, so C was ROF, which had alternating levels of plus and product gates. So in particular, these terms can do factorize. So once we have black box access to these terms, we can iterate over all these terms, obtain black box access to the factors of the ith term, and perform ET recursively on these factors. Yeah. Oh, right. So Oracle access to F, right?
Yeah.
For example, to obtain Oracle access to T1 hat to T1 hat Bx to T hat at Bx, we obtain that from F, right? By just evaluating all the other terms to 0. So for example, over here, yeah, what were we doing? We were just finding A to 2A so that the sum becomes 0. And then you just plug in x1, A2 to AS in B, F of Bx. Right. Yeah. So yeah, we need Oracle access to B2, Oracle access to F for everything in the algorithm. Yeah. And yeah, so once we have found Oracle access to the factors, we can just perform ET on the factors because these factors are equivalent to ROFs of smaller size. So this recursive algorithm constantly like reduces the size of the ROFs, and so this strategy makes sense. It makes progress. However, there is one more hurdle, and the hurdle is the following. So how do we obtain efficient black box access to the terms? By efficient, I mean the following. One query to a term Ti hat Bx must require just one query to F. And why is this? Well, the reason is the following. Suppose that one query to this term requires at least two queries to F. Then one query to any of its factors would also require at least two queries to F. But what are we going to do? We are going to perform ET on that factor recursively. So the factor is Qij. Now that Qij would be our new F. And when we perform ET on that recursively, what would we do? We would find out black box access to its terms, then find a factor of its term and want black box access to that factor. But in the recursion, one query to any factor of any term of Qij would require at least two queries to Qij, therefore at least four queries to F, right? So the number of queries to F blows up with the depth of the recursion. And the depth of the recursion can be as large as n. So if one query to a term required at least even just two queries to F, would end up with an algorithm that is exponential running time. So one query to a term must require just one query to F. And this is the third and final hurdle. So now that I've talked about the hurdles, let me quickly talk about how we overcome these hurdles. So recall that the first hurdle was that the Hessian determinant of C might become 0. In the example that we saw was this ROF x1, x2, x3 plus x4. Now notice that in this example, there is a variable directly connected to the topmost plus gate of the ROF, right? So what we show is that this is the only case in which the Hessian determinant can be 0. That is, the Hessian determinant of C is 0 if and only if there is a variable connected to the topmost plus gate in C. Now, analyzing the Hessian determinant of an arbitrary ROF, and in fact showing that it is just non-zero is one of the main technical components of this work. So the proof of this claim is obviously involved. But what I'll do is I'll give you a very high-level proof sketch of what we do over here. So observe that the Hessian of C is a block diagonal matrix. Whose blocks are H1, the Hessians of T1 to the Hessian of TS, because T1 to TS are variable disjoint. And because of this reason, it is sufficient to prove that the Hessian determinant of Ti is non-zero and degree of Ti is greater than or equal to 2. The degree of Ti is greater than or equal to 2 because there is no variable directly connected to the topmost plus gate. So what we do is the following. We carefully pick a variable x depending on the structure of the Ti and show that the degree of x in the Hessian determinant of Ti can be at most r for a number r which also depends on the structure of Ti. Then we write the Hessian determinant of Ti as a univariate polynomial in this variable, with its coefficients being polynomials in x minus the variable x. Then we show that the leading term, that is x to the r times hr of x minus the variable x, is a product of sub-ROFs of Ti and the Hessian determinants of sub-ROFs of Ti. Now sub-ROFs of Ti are obviously non-zero. So to show that this leading term is non-zero, all we need to show is that the Hessian determinants of sub-ROFs of Ti are also non-zero. Okay, so that depends on the Hessian determinant. So basically what we are doing is we have picked a variable x, a special variable x, and we are writing the Hessian determinant as a univariate polynomial in x. So hr of x minus x is just a leading coefficient, but now since we are writing it as a univariate polynomial, the leading coefficient is in all the other variables. Yeah. So this also crucially depends on how the structure of Ti. So all we need to do to show that this term is non-zero is to show that the Hessian determinants of the sub-ROFs of Ti are non-zero. But the sub-ROFs of Ti are just smaller ROFs. And so by induction, we can argue that those sub-ROFs have non-zero Hessian determinants, and therefore this leading term is non-zero, and therefore the Hessian determinant is non-zero. The proof is basically an inductive proof. Yeah, I'm skipping over a lot of details over here. So, but this just handles the case when the Hessian determinant is non-zero. That is when there is no plus gate attached to there is no variable attached to the topmost plus gate. So what do we do when there is a variable attached to the topmost plus gate? So recall that we made this assumption that every plus gate in C has at most one variable directly attached to it, right? So without loss of generality, assume that this variable is xn, otherwise just permute the variables of C. Then since there is just one variable attached to it, in C minus xn, there is no variable attached to the topmost plus gate. And so from the claim I just showed you, the Hessian determinant of C minus xn with respect to C minus xn is non-zero. And what we do is we just work with this Hessian determinant. Okay. So that was an assumption. And we're like, okay, one quick reason is the following. Suppose there is an entire linear form attached to the topmost plus gate. We are only working with equivalent polynomials, right? So let's say the linear form is x1 plus x2 plus x3. Just translate x1 by minus x2 minus x3. So now the linear form is just x1. This is fine with us because we are working with equivalent polynomials, right? So the transformation that I just applied is an inverted matrix. So we just absorb that inside A. Yeah. So this is without loss of generality. So the Hessian determinant of C minus xn is non-zero. And what we show is this. For a random n cross n matrix, the Hessian determinant of f of Rx with respect to x minus xn is related to the Hessian determinant of C minus xn. So basically, what we wanted to do was we wanted to use the Hessian determinant of C to obtain information about A and B. But now we would just use the Hessian determinant of C minus xn to obtain the same information. So the message is essentially without loss of generality, assume that the Hessian determinant is non-zero. Because if it is zero, there is a workaround. So now that we can assume that the Hessian determinant is non-zero, let's overcome the second hurdle. And recall that the second hurdle was that the Hessian determinant is non-zero, but not all variables may be present in it. So to overcome this hurdle, what we do is the following. We characterize most of the essential variables of the Hessian determinant by studying some special structures in the ROF, which we call skewed paths. So let me define what skewed paths are. Yeah, so there are some essential variables. So there are some variables, and we are not sure whether they are essential or not. We can't prove either way. Like we suspect they are essential, but we can't prove it. But yeah, I mean, we don't need it. So yeah. So a skewed path is defined as follows. A path from the root of the ROF C to any plus gate Q in C is called a skewed path if every product gate on that path has just two children. One is a variable and another is a sub-ROF containing Q. So for example, in this ROF, there are two skewed paths. The first skewed path is from the topmost gate to this gate Q. Now, moreover, every skewed path can be uniquely identified with a monomial. This monomial would just be the product of variables that appear along that skewed path. So for example, this skewed path is completely identified by this monomial x1. There is one more skewed path in this ROF, and it is this path. So from the topmost gate to Q prime. And this path is identified by the monomial x1 times x2. So now this plus gate Q prime also has a variable attached to it. So we'll call that variable along the skewed path x1, x2. It also has a quadratic form x3, x4 attached to it. We'll call this quadratic form the quadratic form along the skewed path x1, x2. And we'll just call these two variables x1 and x2 as variables on the skewed path x1, x2. So now that we have defined what skewed paths are and established this terminology, let's see how they are useful. So we are able to characterize the essential variables of the Hessian determinant using skewed paths. What we show is the following. all variables other than the following: the variable connected to the topmost plus gate of C, the variables in the quadratic form connected to the topmost plus gate of C, all the variables along the skewed path, so variables like x5, and the variables in quadratic forms along the skewed path, so variables like x3 and x4. These are the only variables which might not be essential for the Hessian determinant. And however, recall that to make the terms of F variable disjoint using Kayal's approach, we needed all the variables of the Hessian of C to be essential for the Hessian determinant. But only some of them are essential. So how do we handle this case? So at a very high level and skipping a lot of details, what we do is the following. We first use Kayal's approach to find an invertible matrix B so that the terms of F of Px are as variable disjoint as possible. What do I mean by this? All parts of F of Bx except the affine forms corresponding to these non-essential variables become variable disjoint. So now there are only some parts of F which are not variable disjoint. We need to handle them somehow. And what we do is for this is the following. We should first show that every variable on a skewed path. So for example, every variable like x1 and x2 is a factor of the Hessian determinant of C. Therefore, the affine forms that these variables map to under the action of Ax plus B are factors of the Hessian determinant of F. And what we can do is we can just find these affine forms by factorizing the Hessian determinant. Once we have found these, we update the matrix B to map these affine forms to variables. So earlier, every skewed path in C could be identified by unique monomial. Now we can also identify every skewed path in F of Bx with a unique monomial. And now these monomials act as sort of unique markers for the affine forms corresponding to the non-essential variables, and these unique markers sort of help us in handling those affine forms. Yeah, so this is very hand-wavy, but yeah, this is what we do, and this is very technical. So I'm skipping a lot of details. How much time do I have? Okay. So now let us finally overcome. Yeah, it's fine. Yeah. So now let's see how we overcome the third hurdle. Recall that the third hurdle was how do we obtain efficient black box access to the terms of F of Bx, that is to T1 hat Bx to T hat S Bx. Now let the variable sets of these terms be x1 to xs respectively. The first task is to find what x1 to xs are. And here's how we do it. So observe that if I is not equal to j, then for xi in the variable set xi and xj in the variable set xj, the double derivative of F of Bx with respect to xi xj is just the derivative of it's just a derivative with respect to xi of the derivative of t hat jbx by xj, right? Now t hat jbx does not contain xi, so its derivative with respect to xj also does not contain xi, and so the entire derivative is 0. That is, if you pick a variable from xi and a variable from xj, and xi and I and j are not the same, then the double derivative of f with respect to xi xj is 0. And this already gives us some indication that probably by using double derivatives, we can find out the variable sets xi and xi to xj. So what we prove is the following. In fact, this similar claim has also appeared in the literature before. So create a graph G as follows. Its variable, its vertex set is just a variable set, and its edge set is created as follows. We add an edge between the variables xi and xj if and only if the double derivative of f of bx with respect to xi xj is non-zero.
But for variables in the same term, it can be 0, right?
Yes. Okay. So if it were not 0, then all you have to do was the following: pick xi, pick xj, check if their double derivative is non-zero. If it is non-zero, they are in the same variable set, right? But as you said, the double derivative might be 0,
Yes.
which is why we need to create this graph. Once we have created this graph, what we can show is that the connected components of this graph are x1 to xs. So basically what can happen is you can, let's look at inside x1. You can have 3 variables, x11, x12, x13. The double derivative with respect to x1 to x13 is 0. but the double derivative with respect to x1 to x11 and x11, x13 won't be 0.
Right.
So they are still in the same finite component. So yeah.
In a component form for sure.
Yes, that's what we show in this claim.
Oh.
I mean, so also this claim for ROFs has appeared in the literature before, but we are doing this for polynomials equivalent to ROFs. And so yeah, once we obtained these variable sets x1 to xs, let's see how we obtain black box access to a term. So let's just focus on the first term, t hat 1 bx. Its variable set is x1. So what we do is the following. We replace x2 to xs by 0. So we evaluate f of bx at x1 and all zeros. What does this give us? Since x2 to xs are 0, this entire sum, the sum of the terms t hat 2bx to t hat sbx, that would become a constant. Let's call that constant gamma. So now we have obtained black box access to the first term plus gamma. We want a black box access to the first term. All we need to do is somehow find gamma and subtract it. So now let's see how do we find gamma. So what we show is the following. Let us suppose that a degree of t1, which is the same as degree of t hat 1 bx, because that t1 was a term of C corresponding to t hat 1 bx. Now suppose this degree is at least 3. Then if this degree is 3 and t1 hat bx factorizes as q11 to q1m1, then at least one of these factors is also a factor of the Hessian determinant of t1 hat bx. Now, okay, over here there's a restriction that degree is at least 3. But all the terms that have degree exactly 2, well, they are quadratic forms, which we have already handled while overcoming the second hurdle. So forget about that. Yeah, so now suppose that the factor q11 is also a factor of the Hessian determinant. And for the sake of simplicity, let's assume that f is an algebraically closed field. That is, every polynomial, every non-constant polynomial has a 0 over that field. I mean, this is not required. I'm just assuming it for the simplicity in the talk. Okay. Then there exists an A1 so that Q11 evaluated at A1 is 0. And thus T1 hat plus T1 hat Bx plus gamma evaluated at A1 is 0 because T1 hat Bx has a factor Q11. So now we have now we have gamma and we can subtract it, get black box access to T1 hat Bx. What's the problem? The problem is, sure, one of Q11 to Q1m1 is going to be a factor of the Hessian determinant, but it might have also other factors as well. So what if you pick the wrong factor? You might get another gamma. So what we do is the following. We iterate over all the factors of the Hessian determinant, find a Q, let's say the factor is Q, find an A1 so that Q of A1 is 0. Then set beta to be T1 hat Bx plus gamma evaluated at A1. Then we perform the following check. Is T1 hat Bx plus gamma minus beta equals to 0 or not? If it is, set gamma to beta and break the loop. Now, okay, so this step assumes it's algebraically closed because A1 exists, right? Yeah. Okay, so what we do over an arbitrary field is we reduce this. So instead of finding roots, we reduce it to a problem of solving a system of linear equations. Yeah.
But that step will be discrete.
Right. Yeah, but I mean, that's a little involved. So I'm just working on algebraically closed fields over here. Now, as we saw before, if by some chance we were lucky and Q was a good factor, Q1j, then beta would be gamma and we would be done. But what if before encountering any good factor, we encounter a bad factor? And what if also for that bad factor, we end up passing the test in step 4? Do we get a beta which is not gamma? Because that's a bad case for us, right? We pick a bad factor, we pass the test, and still beta is not gamma. Well, we show that this is not possible. If the test passes, then beta has to be gamma. Sure, you might have found this beta using some bad factor, but we don't care about the factors. We just care about gamma. So we are fine. And this is all. So this is how we overcome the 3 hurdles. And as we saw before, if you overcome the 3 hurdles, this is the recursive approach that we can use. Now let me just quickly end with some open problems. The first open problem is doing P for univariate substituted ROFs. So univariate substituted ROF is an arithmetic circuit which is very similar to an ROF. The difference is as the following. In ROFs, the leaves were labeled by variables and constants. Now in a univariate substituted ROF, the variables are labeled by univariate polynomials and and constants, but every variable appears in just one univariate polynomial. Now the reason for studying this is that P for ROFs only generalize QFE for complex numbers. P for univariate substituted ROFs would generalize QFE for arbitrary fields. The second problem is ET for sparse polynomials. And the problem is given an n-variate polynomial f and a parameter t. Check if f is equivalent to a t sparse polynomial g. If yes, output an invertible matrix and a translation vector that gx is equal to f of ax plus b. And what we would like to do is either find an efficient algorithm or give a hardness result for this problem. And the third problem is learning random formulas with polynomially many leaves. Now, ET for ROFs is learning random formulas with at most n leaves. We would like to do this for more leaves. Yeah, that's it. Thank you.
So I'd like to thank Bhargav for the talk, and the floor is open for questions. Anyone online has any questions? If no, we can then wrap the session. Thank you.
Oh, okay. What do you mean by a probabilistic version of equivalence? I mean, okay, can you elaborate? What do you mean by a probabilistic version of equivalence? Okay, so what? Okay. So what you mean is the following: f is approximately equivalent to g if there exists an invertible matrix A and a translation vector B, so that f of x is approximately equals to g of ax plus b, right? I mean, I don't think something like this has been studied. Does that answer your question? Yeah. Okay. Yeah.